Yeah, indeed. Hi, everyone. I hope you're doing fine. Yeah, okay, so where were we? We are the not very numerous six. I think people have a habit of joining in a couple of minutes after the class begins. But anyway, okay, seven. We just finished, we're in the middle of the Ray-Knight theorem, and we've done the crucial step in some ways. We have proved the 2-point estimate. I guess it's captured in this result, really. It's expressed in terms of a transform, but it's saying if we condition on the normalized number of down crossings at height x being u essentially, then the distribution of the normalized number of down crossings at height x plus h is given by kicking off a Brownian motion in the plane from a location given by the square root of the conditioned level at height x, and then evolving it for time h, and then it's the square of that. So that's the 2-point projection of the Ray-Knight theorem. Okay, and that's the heart of the matter, really. Well, one has to be careful about how to finish this off. Basically, though, we're in a situation where we have Markov processes from the representation. Okay, so there's two sides. There's the planar Brownian motion side, the square of that. That's a Markov process. Easy to see that. And then on the downcrossing side, the kind of representation we've looked at means that in the relevant sense, we have a Markov process as well. So I should probably just say a few words about this. I'm not really going to dot all the I's and cross all the T's on this, but okay, so my notes say, given the Markov nature of the two processes and their coincidence in two-dimensional distributions, the finite dimensional distributions coincide as desired, except for I'm reading the wrong page. I see that's the conclusion I should be reaching. So, so in terms of closing out the proof of the Ray-Knight theorem, given this 2-point information, yeah, so just want to say at least a few words that gesture in the right direction towards this. We have processes that are continuous, that we are trying to show are equal on the basis of the 2-point information. One of those processes is the squared Bessel process, the square of the planar Brownian motion, and the other one is the local times indexed by the height. So t here is given. Oh no, sorry, t isn't given. T is the hitting time of 0, beginning at level A. Yeah. So these processes are continuous. So okay, how did we literally establish that? We definitely, I think, for both processes, did most of the work to establish this. Certainly for the construction of Brownian motion, I think I can claim that we established uniform continuity. And then as for the local times, I actually slightly forget where we got to in that, but the local times in the x-coordinate have a Holder 1/2 minus continuity that arises from the, essentially from the Holder minus 1/2 continuity of half minus continuity of Brownian motion. So it then suffices, given that information, to check we have convergence in finite dimensional distribution. It suffices to show that, if I take an increasing system of levels that fit in our framework, that's supposed to be a 2 up to xm, but that stops below level A, so that's where we started, right? String of levels like this. Yeah, okay, well, we can look at the vectors, the random vectors, thus indexed for local time. and for our squared Bessel process. So it's enough to show those are equal in law. But the view is the reason why the 2-point information we already have is going to deliver that is because this is a Markov process for either process. In terms of the evolution of the x coordinate. So that's something that's obvious for the w side of things. It's inherited from the Markov property of the square of a planar Brownian motion. So we just need to say something and to gesture towards this statement's validity, that this regarded as a process in this k parameter is a Markov chain. So this goes back to our representation. Probably doesn't help you very much to say it's lemma 6.31. It would take me a while to scan back through the notes. But anyway, I think it was that's the basic down-crossing representation formula. The dnxk is basically a function of what was going on at the level below somehow, and various random variables that are independent of, well, everything really, including all the lower levels, and including, I think, dnx k minus 1. So, yeah, well, okay, on that basis then, well, I just want to kind of say that's it, really. I'm not really doing this proof very carefully. It's not really captured my interest to do that somehow. We have this basic transition formula for the squared Bessel process side of things that, you know, the kinds of, I suppose I'm just saying here that the 2-point information is correct in the sense that if I condition on a location for this process at stage k, then the evolution is given by this kind of formula. So that's saying, I think, that the 2-point information coming from the lemma we proved last time is correct in describing the evolution of the squared Bessel process. So yeah, as I mistakenly said earlier, given the Markov nature of the two processes and their coincidence in 2-point distributions, the finite dimensional distributions coincide, and then there might be some convergence in law niceties that are taken care of by lemma 6.37 in the text. But this, in essence, completes the proof of the Ray-Knight theorem. There is a more careful treatment of what I've been really just gesturing towards in the text. I'm not particularly inclined to elaborate details that I see as being a little bit picky in a way, not very conceptually significant. So there is an application. I mean, we've worked hard for this, and despite some gaps in our proof, we have, I think, carefully addressed the more fundamental aspects of the proof, particularly the 2-point result. So it's nice, obviously, before moving on to something else, to at least gesture towards why the result might have some utility. I'm not going to do a great deal in that regard, to be honest, but let's at least look at something. So let's just go back to the basic context, of course. Starting at height A, we stop when we hit the x-axis and record local time in this accompanying chart, whatever it's doing. And then we have a description from the Ray-Knight theorem that's valid as x evolves upwards towards level A from 0. So then we have this description in law that we've seen. So, you know, one thing we can do with this is to make more simultaneous statements about the local times. The local times are very nicely coupled together. If I take a Brownian motion, I could take the example already there, I suppose, then the local times are an interesting coupled family of objects where there's obviously relationships, what indeed we're exploring, between different heights and the local time you have at them. And so one question you can ask then is, if we got an understanding at given time that for a given x such as 0, if we have a process starting at 0, I think we've proved, or anyway, the text parallel treatment of the down crossing reached the conclusion that the local time is positive for all, for x being a given value. Okay, this is a probability 1 statement. But I mean, we can ask simultaneous statements. Is this true? What's the probability of this? We have an uncountable collection of copies of different local times coupled together in a single probability space via our particular Brownian motion that's top left in this picture. It could be, in principle, any probability. It's not predicted by the fact that a given Lx of t is definitely positive that this has any particular value, but in fact it is with probability 1 that they're all positive, and then that's just coming from the fact that over in this representation there's probability 0 that a planar Brownian motion, it never hits 0 almost surely, so its distance is always positive. So anyway, that's just a minor example of something that we learn from this representation. Then we have an application that's also related to simultaneous description. So another application is that I won't go through, but I'm just pointing it out there as a direction and a useful outcome. So almost surely we can make a statement simultaneously about the dimensions of our level sets. We've discussed a particular level set, of course, 0, called it capital Z. Capital Z was the 0 set of the Brownian motion, but we can hit other levels as well. This is the statement. Yeah, I'm not going to actually try to justify that, but that is an application of the Ray-Knight theorem. And in fact, this equality holds, in fact. That is true. I'm just following the text when it says this. This is via Kaufman's dimension doubling theorem, which in all honesty, I haven't really looked into, but it is in the text. So that's in the text in chapter 9. So that could be a direction for further reading if you want, and it could be, keep thinking about the presentations at the end of the semester and what you want to talk about. That would be a possibility if someone wanted to go that way. Right, so that kind of concludes the discussion of Brownian local time. We might come back to it in certain guises. We've certainly got it as an important example of a random double staircase, and we see these connections we'll come back to quite quickly. In fact, for example, as I say, the way in which we in a sense with Brownian local time, we petition the real line into equivalence classes according to the value of Brownian motion. And so the equivalence classes are the level sets, and then each one, say in a compact window, gets a certain size. So we have a partition of a particular interval into level sets, and then they all kind of are disjoint, but in some sense compete in units offered by by the measurements made by the local time. So that will be an idea that I'll come back to, and that's certainly part of the story of these random Devil staircases, that at times they form a kind of a coupling of uncountably many copies that represent a space collectively in some sense. So we've reached a particular moment in the class. We have in principle something like 6 chapters for the class. I don't really know that they'll all get a great deal of attention. The first one was simply the intro, in which we just summarized and surveyed. In fact, in a sense, I'm repeating the intro very briefly now by re-summarizing the main examples we'll look at. So the BLT we've just concluding. Okay, so then let me just briefly recall directions. What we'll do next is to, I don't know if I actually said it was chapter 3 in the introductory material, but we have ideas around IID sums. I'll just almost immediately write the chapter title, so I won't write it down, but IID sums and things, ideas around renewal theory, and the kinds of Devil staircase we get in the simplest examples, really, where we just have return times that are offered according to the values of an IID sequence. But then I want to kind of join that topic up with the concept of fractional random walk and fractional Brownian motion, which is something I worked on with Scott Sheffield about 10 years ago. So I'll draw some connections there and draw those into a single chapter, this chapter 3. And then the other kinds of things we could look at in the class in terms of the main driving examples are biased walking disorder. So that's the phenomenon of trapping in a disordered environment, getting waylaid in traps and having flat sections in a random Devil staircase represent sojourns of a particle moving in disordered manner and then getting stuck in traps. Then we have potential to look at some discrete Fourier analysis and dynamical percolation. That could be a nice direction for us. That's critical percolation on the honeycomb lattice has critical probability, has probability 1/2, and one can have a dynamical version of that and couple together in that manner in a natural way uncountably many copies of critical percolation on this lattice with a natural time dynamic. And then there may be exceptional moments that defy the static equilibrium, a 0 probability for having infinite structure. Indeed there are, and then that gets into an exceptional set, a bit like the 0 set of Brownian motion. So we can ask about Hausdorff dimension. These questions have been analyzed thoroughly. We can look at the work of Petter, Schramm, and Garbon, Petter, and Schramm. And then we can also build in connections to random Devil staircases if we wanted, because there was a local time construction that I did with Oded and Garber at one stage, so that could be a direction for us. Then there's some KBZ connections, maybe Kadar, Parisi, Zhang, universality. I won't rehash that now, I think. And then there's one topic that actually probably won't really form a part of my lectures, but I think Ruben has been looking into an interesting direction in which we see random Devil staircases in a kind of idealized problems in celestial mechanics. And we were looking at a monograph of Jürgen Moser from maybe the early 70s, and maybe there's some interesting directions there. That could definitely be a direction for presentations. Yeah, okay, so anyway, it's just sort of a stopping point along our journey and a reminder of where we've reached and where we're going. It's not, is it distracting anyone? There seems to be some noise going on in the background, I can try and close a few windows if it's a problem. To me, it sounds slightly distracting, but shout out if it's a problem and I can try and move or something. Yeah, all right. So, well, all right. I guess before I start chapter 3, I can ask any questions. Are there any questions?
Yeah, I have one question. We might have already talked about this, and I might have forgotten, but I think at the very beginning of talking about local time, you said that local time also happens to be the running max of a different Brownian motion on the same space.
Oh, yeah. So we kind of gained some access to that topic when we talked about. It is the case in law that the running max. The process that I'm sort of drawing there as the running max has the same law as the process. What's the notation? L 0x. That's Levy's theorem, which I forget, we didn't actually prove it, right? I forget what we proved and what we didn't now. That is something that so I forget that one of these statements we proved and the other one we didn't. It's proved in the text. Now, is your question though, is there kind of a coupling? Or
yeah, I think
well,
maybe you said this or maybe I heard it somewhere else, but I think there actually is another Brownian motion coupled to the original one, such that the local time is the running max of it.
Yeah, I mean, we sort of did things related to that, right? I mean,
Yeah, I guess we did that like in the pre-limit, kind of.
Yeah, isn't it somehow that you want to say that this picture has embedded within it the notion that perhaps another Brownian motion, we're looking at its absolute value at least. I mean, when we look at, if we call this one B, oh, well, then it's bad notation. This is another Brownian motion, okay? So M minus B is in law equal to this. Well, anyway, if it's labeled B prime, then it absolute value, then B prime can be. So explicitly, I draw this picture, then I sort of draw things relative to the maximum, i.e. I sketch M minus B, and then that's necessarily positive. But then I suppose what I do is I just flip for every excursion, there's countably many, plus or minus 1, and then I kind of draw, so, you know, M minus B looks like this, and then there's countably many excursions and they're labeled +1 or -1, and then that obviously then dictates which way we go, and then that a Brownian motion, let me call it W at this stage, and then the view would be that the local time of that is the yeah, well, then that's for W.
I see. Okay, yeah.
Yeah, now quite how much, I slightly lose track actually. We came pretty close to proving that. There's a theorem of Levy, and I think it's even maybe that you can consider it jointly process and local time at some level. It's in the text anyway. I think morally we basically proved that.
Okay, cool. Yeah, thanks.
Okay. Can ask questions about global or local aspects before we start getting back into the detail of something. I'm going to go into a topic. I think globally speaking, the next topic is one of the moments in the class where there's maybe the more direct opportunities for kind of engagement and research, I would say, well, obviously what I've done up to now, these are pretty classical results, so they don't really raise very direct research questions. And as I look at the other topics on screen, I would say, well, I think Ruben is actually investigating something with the topic 7 that could actually be quite fun. The other ones, 4, 5, and 6, I would say it's at the level that if people want to get engaged in research on these topics, they could be good opportunities, but they wouldn't necessarily be problems that would be right from the get-go. They would probably be, being inspired with class material as a point of departure for more reading that could ultimately lead into research. But I would say probably the topic I'm going to do next is one where there's a more direct. Here are some simple open problems that adapt what I'll be talking about, and can we start thinking about how the ideas from the lectures will adapt. I mean, in a sense, chapter 3 is split into 2 parts, and I'm talking more about the second part. But anyway, globally speaking, that's kind of an indication. So, I mean, the kinds of ideas, I'm not quite sure exactly what to call the chapter, but we're talking about independent return times. It's basically going to be a pretty explicit example of random double staircase, and I feel the need to at least gesture towards how in the standard example things work. It's connected to the probabilistic topic of renewal theory. I think the view of this class number is it's supposed to provide people who are doing a PhD in probability with some background, and in the sense there are certain things that you should probably know at least something about in order to, to graduate in probability, so to speak. And renewal theory is definitely kind of one of the topics that fits in that framework. Is something that it's good to know at least a little bit about. And fractional random walks, I'll explain what that means. Let me focus on the first and second elements in the title, perhaps, to begin with. So let me perhaps riff off of the example we've just been studying and locate it in a more general context. So let's back up to a discrete example of a simple random walk with its independent plus or minus 1 moves according to independent coin flips, doing its stuff and coming through 0. Obviously, that's a discrete counterpart to what we've been studying occasionally. I suppose we did study it directly. So, the 0 set is, if it's called Z again, then that's obviously a random subset of the natural numbers that contain 0. We start our process at 0. Then we're considering, beginning from that point, the further points at which we return. S is the actual simple random walk, kind of S for sum as well, because the walk is obtained by adding the independent increments. So, okay, so I mean, to be explicit, this set has, of course, a very specific form that's related to what's called renewal theory, in fact. So Z simply consists of those elements of the natural numbers that take this form. So this is an IID sequence, xi, of course, with the law of, I just have to tell you what the law of one element, of course, that is, of course, the law of a return time. And if you start at 0 at a particular time 0, say, then what is the distribution of when I am next at 0? That is the law of x1 and of all of the x's in the sequence. So you see, at some level of detail that's useful for just locating the topic in the framework I want to be in, we have this type of statement. Indeed, we can say that this is true in more precise terms. This probability is tilde of a c t to the minus a half for some t, for some c, where tilde means the left and the right hand sides ratio converges to 1 in the limit of high t. So let's just quickly check, at least to give you an informal argument for why that power holds. If this process is going to go up or down, let's assume it goes up by 1 unit from its beginning, and then it is on a ride of random length before it comes back to 0. And we want to check how long that is. We're interested in the possibility perhaps for t relatively high, that the excursion endures for time at least t. And, you know, the way I would put this to give you just a sense of why this power 1/2 is true is that basically the probability of reaching a height of t to the 1/2 before hitting 0 is behaving like t to the -1/2. And the reason for that is, you know, a martingale argument, an argument we've given, in fact. The probability of a random walk hitting height h, an integer before 0, is this probability 1/h of the scenario of reaching here. We saw that argument, okay? So, you know, basically, you know, at least one way of reaching time t is to manage to drift off to height root t without hitting 0. Something, as I say, happens with probability of order t to the -1/2. Having got there, you know, the quadratic scaling of a random walk and the square relationship between space and time means that the time left to come back down and hit will be of order t. So, in other words, for example, with positive probability having reached that height, we should be in good shape to return at a time later than t. So that's a bound in one direction. That would prove that perhaps with the theta notation, that's okay. That's a lower bound on the probability of this kind of event. As for the upper bound, well, it's just a question of arguing that it's rather painful, I think, to not get into this circumstance. If you choose not to go as high as t, then you are, you know, with a t being relatively high in some sense, I can draw a Brownian motion. It's going to have to stay in a channel like this for many units of its natural. There's a natural square relationship between vertical and horizontal here, and there's going to be many pockets like this that we're going to have to endure before coming back here at time t. It's not really a rigorous argument, and I don't propose to give one. I don't suppose it would be terribly difficult to do that, but that's an indication for why we have this 1/2 power, okay? So that then can locate us in a broader framework, if we want, where that power is replaced by another power that's perhaps between 0 and 1, reflecting the heavy tail nature of the beast when we talk about these random devil staircases. Let's just stick with this example. I mean, in a sense, I'm rehashing material that was properly the subject of the last chapter in a way, but let's just explore this a bit further. So if I just look at this discrete example and I look at the amount of time you spent at 0, this is my, I tend to use this notation to mean integer interval. So those are the integers between 0 and x that lie in z, i.e. The random moments of time at which our simple random walk s is at 0. And the cardinality of that can be measured. We can keep account, in other words, of how much time you spent at 0. And then that will accumulate in some manner and it will give me each excursion, each flat piece, each plateau is an excursion. At time n, we should have reached a height of order root n. This is the overall picture we'll have. So it's tempting then to scale that picture, just as we scale random walk into Brownian motion. We should have a scaled RDS, random devil staircase, and that should be converging in a suitable limit to the local time we constructed at 0. So anyway, just though to emphasize ideas in this way, I mean, having identified a power of n to the 1/2 for the y coordinate, it's natural to bring that back in to try to get a degree of stability in the high n limit. So I can kind of plot this function where x is playing the role of a continuous notion of time. So I need to, I just do a silly little integer rounding trick so that I can speak of continuous time x. So this could be now viewed as a map from the the half infinite real line into the positive reals, or in fact into a squeezed up copy of the positive integers. So then you have this picture that is in some sense the generic picture for the class, the random devil staircase that's becoming somewhat fractal in its nature. So that then, of course, I don't know if we've carefully proved this, but morally we've done the work to identify this fractal. This staircase is the distribution function of the zero, of the local time at zero of a Brownian motion. So this raises, though, some questions. If we view this topic not so strongly through the lens of the particular example, but rather view these devil staircases as coming out of the basic framework of this problem, the problem here can, of course, be stated without reference to simple random walk. The basic data in the problem that you see here is simply the law of x1. Forget the fact that it's a local time and just treat it as a law on the positive integers, or indeed a law on the positive reals. What condition do I have to put on the law in order to get some sort of random devil staircase out at the end? So that raises, I suppose, two questions. If it's going to be the kind of heavy tail situation that we see here of t to the minus a half, what values might replace 1/2 so that we have some cousin picture of a random devil staircase scaled in the limit? And then there might be another question, which is related to the meaning of the symbol, the approximate symbol that's written in the penultimate line there. In this particular example, yes, it could become a tilde and be a rather strong notion of regularity, but one can ask the question, if you're dealing with a particular exponent 1/2 or some other exponent, what condition of regularity might I need to put on the tail in order for us to have a setup in which we might hope to take a distributional limit of the RDS becoming the scaled RDS in the sketches I drew. In other words, what meaning does the approximate sign have to have in precise mathematical terms in order to take the kinds of limits we see in this picture? Okay, so let me write, I suppose, at least a sentence in these notes to represent that verbal discussion. Under what a condition on the law of, it's just really this one law that's at stake now for x1, it's an IID sequence, may we expect a limit in law for this scale RDS, this scaled function, random devil staircase? And you can see here I'm posing a question that's pretty natural, right, given the actual guiding theme of this class. I mean, this is clearly a very natural class of objects that give rise to random double staircases. You could imagine more complex structures, of course, with dependencies between the consecutive x's, or, there could be contexts in which such a structure is natural. But given that from the simple random walk example, we have a non-trivial nice example of an RDS, it's natural to broaden this out to this family and ask these questions and make sense of this theory. So the relevant theory is the theory of heavy-tailed random variables in terms of what exponents we can expect. The short answer to the exponents is anything between 0 and 1. A heavy-tailed situation, we can expect to have some sort of counterpart picture. And then in terms of whether we can have the convergence, there the theory of regular variation is what's relevant. And here again, I think this is not something that you see every day in probability, but it's an important corner of the probabilistic world, the theory of regular variation. And I feel that by saying something about it at this stage of the class, I'm meeting this aim of communicating to you important overall arching ideas that you may not be able to remember very precisely 2 years later, but you know, if you remember the main points about this and know where to look, that will be valuable. So yeah, okay, so there's a nice text. I have managed to get hold of it electronically, and I can, I guess, make it available, or at least the relevant chapters. So it's Bingham, Goldie, and Turgles wrote a lengthy text called Regular Variation. So I suggest that we begin by reviewing some ideas from this. Now, despite what I just said, or maybe related to it, the notion that I'm explaining or gesturing towards a topic, I've been in somewhat two minds about how deeply to go into this theory. Let me state some of the main results, and then I will prove certain things. And it bridges into the second part of this chapter, the fractional random walks, my presentation. It will not nonetheless be a highly concentrated or technical discussion of this. I'm going to begin with, so I'm going to make some definitions. It's going to be in a way slightly technical, but it's all somehow undergirded by the desire to make sense of these kind of pictures. Under what circumstances might we expect the IID structure in the discrete case upstairs in this picture to transmit via appropriate scaling to something that actually has a distributional limit in high n? You see, there's a notion of a high n limit here. In law, in some appropriate topology, to settle down to, in this case, the Brownian local time distribution function. So this is what's undergirding the definitions that are coming up. So, okay, so here's a pretty basic definition that connects to laws. I think all of my laws are going to be on the real line. And in fact, many of them will be on the positive real line. So I won't, it's understood that these are probability measures on the real line. So a simple definition says that two such laws are said to have the same type that just means that if I go ahead and realize the laws, as I have random variables whose respective distributions are the laws, let's call those capital X and capital Y, then I can couple together couple X and Y, so I have a single probability space on which X and Y are well defined and have these laws. So then we can explore relationships between them. So that this can be done so that they have this relationship. So if I took a standard Gaussian law for mu, mu could be a arbitrary Gaussian one-dimensional with a different mean and a different variance, because I have the capability to do those dilations and translations in order to deliver that. So there's a sense of the normal type sitting on the real line. So here's a nice definition that is very related to the questions we want to ask. If I take a non-degenerate law, that just means that it's not, it just means its support consists of more than one point. It is not a representing a constant random variable. So we have the important concept of stability, which is more than one way to define it, but here's one way. If I have two random variables that share the distribution mu and they are independent, then this implies that when I add them up, I haven't left the type of mu. Or maybe that's a technically abusive definition. I mean, of course, I mean the law of x1 plus x2 as the type of mu. So that is equivalent to, and this brings us a little closer to our context. So a law is stable if and only if for any n, it's kind of an induction from what we have. If I take independent copies x1 up to xn, random variables, and they each have the law mu, then what happens if I do exactly the kind of thing we're interested in, kind of forming a random walk rally with these as the increments? Okay, so if I add up the things, then this has the type of mu. So this is clearly implies the earlier statement. It's stronger, but it also clearly follows from the earlier statement because it's just a simple induction. So this means explicitly that the law of the sum is equal in distribution to this kind of scaled copy of mu. So, you know, there are some choices of an and bn so that you see this. So are people comfortable with that definition? Can anyone perhaps, well, you can answer that question, or maybe someone wants to shout out with a couple of examples of stable laws. Can you spot something? Well, the normal, as I've kind of already said that, right?
Maybe a Cauchy distribution.
Yeah, I think that's correct.
Statement.
Yeah, that's correct. I actually have to, yeah, okay. The Cauchy distribution actually, I think, corresponds to one of the extreme cases we consider. Can you just remind me how that stuff goes? What is the actual definition of the Cauchy distribution? It's density somehow. I
think it's the guy with density proportional to 1 over 1 plus x squared.
1 over 1. You think it's 1 over 1 plus x squared? It's not something like, I vaguely remember, it's not something like that, is it?
No.
Let me see if one of the texts I've got to hand defines it. It is, I think, is it the same as the Cauchy? No, maybe, sorry, you're probably correct, actually, sorry. No, you're correct. So it's, at least in a special case, it's given by this, and then maybe there's a more general case where it's t over t squared plus x squared with a normalization of 1 over pi. So that is, I believe that does fit in this framework. Yeah, that's correct. So there's a convolution property that has this rather strong sense that it's a situation in which if I take n of these independently with this law and divide by n, that has the law of x1. So you kind of a little bit weird in a way that you have independent copies of a given distribution, you add them up, you average, and then you still have that distribution. So that is a special case of what we're doing, yeah. There is a related concept called infinitely divisible, which is a slightly weaker concept. So infinitely divisible, x, or more correctly, perhaps its law, this is a random variable, is infinitely divisible if for any n, I can find a representation for the random variable of this form where these are independent, but they have the same distribution as each other. So the yi are identically distributed and independent. So that's a slightly weaker property because the stability is moreover asserting that x and yi have a certain similarity in that distribution, that they are of the same type. So it's actually, in a way, it's a slightly easier question for me to ask you, can you think of some examples of infinitely divisible distributions? Well, there's more of them anyway. Any takers?
Any normal distribution?
Yeah, that's right. So we can see that from Brownian motion, if you like. Well, we don't have to use Brownian motion, but you know, Brownian motion at a given time has law, at time t, it has law n0t, and we can easily change the mean, and then we can cut that up into pieces. You know, we can divide into n equal time segments and then treat the y's as the increments. And then we will have a normal 0 t over n shared law for the increment. So we won't have the same very special case that we would have exactly the same distribution. And the definition of infinitely divisible makes no claim of similarity between the y1 distribution and the resulting x distribution. With stability, as I say, there is the claim of being of the same type. And we are of the same type in this example, I think, because being normal with one mean and variance is the same type as being normal with another. So there's another basic example. You think about the structure of some famous...
Probably some kind of Poisson random variable.
Yeah. Do you want to develop that answer, which is correct?
Yeah, well, I think from the picture in the first thing, like if you have any Levy process, the same thing works because the stationarity and the independence of the increments means that I can always, if I divide up the time axis into n things, then they're going to be IID.
Yeah.
So if you just do like a Poisson process,
then
you can divide them up.
Yeah, that's right. I mean, it's just the case that, you know, we can build into Poisson processes that's right as well. I mean, the basic, you know, statement is that if x is Poisson of parameter mu, mu is now a positive real, and y is mu1. Mu1 is a positive real, and y is Poisson of parameter mu2. These are independent. Then what is it? X plus y is Poisson of parameter mu1 plus mu2. And this is the kind of structure that is going to give infinite divisibility, because if I start with Poisson of any parameter, one, say, I can couple that to two mutually independent Poisson half random variables in such a way that the sum is equal to this object, and then that splitting can continue all the way down. Of course, when you go all the way down, you end up with an outcome that in some sense is very different from the previous example, because after a while your random variables they're always discrete objects, and the individual random variables in the splitting become zero typically. So the actual form of the representation, but the interpretation of the terms is very different to the previous example, but it does fit in this framework. It's much further though from the concept of stability, because when we do this splitting iteratively, we have definitely a sense that the split individual terms are very, very different in law to the actual accumulation of them. Whereas in the case of the Brownian example, we have in a sense a very strong form of invariance, and the stability indeed of the normal distribution is seen in this example. Yeah, so then you can represent these sort of things, of course, by, as Adam says, by processes. And then you can sort of have a bit of a think about how that process representation is consistent with what we're saying. Yeah, so that's an example. So that's a broader framework. So the kinds of situation, I suppose, that comes up a little bit in our topic is if I went for an example of not Brownian motion, but I went for what's called the Ornstein-Uhlenbeck process. I'm not really going to write formulas. I think the Ornstein-Uhlenbeck process is a process that locally does exactly what a Brownian motion does, but there's a sense of forces that become linearly stronger as you move away from the origin, and they point you back in, and they act as a drift. So Brownian motion will drift away from the origin. This process will stay at a bounded distance from it and have an equilibrium, which is a normal. And then if you were looking at return times in this context, or in a discrete counterpart thereof, you would get yourself into a situation where somehow, well, there would be kind of an end dependence. In the Brownian example, it's just that I rarely have an IID sequence, and I add up the terms in the way we did and scale it. Here I have to work in a kind of more n-dependent way, whereas if this is, I somehow have to explain what n is. I mean, if I do a discrete counterpart to this, but it's done in a way that kind of respects the overall picture, then there's a sense of the return map depends in law on n. I mean, it's an IID sequence for given n, but then as n changes, it changes. So that gives you access in the limit to a somewhat broader class of random Devil staircases, which are basically ones coming out of the theory of infinitely divisible distributions rather than the more restricted theory of stable ones. So it's easy to show anyway, if we get back on track with the stable laws, which are somehow what I want to focus on. So the statement that Y, or perhaps technically I should say its law is stable, is true if and only if there exists a law mu. So that is not necessarily the law of Y, such that if I go for an IID sequence, yeah, okay, so did I mean mu? It's possible I meant to write nu. I suspect I meant to write nu there. So does there exist a law nu such that if I define an IID sequence of terms that have that law and then add them up to form a walk really, S, then there exists normalizations of this that bring it back on scale somehow, and then it converges to Y. So, all right, when we have, this is, I didn't actually, I think it is easy to prove this, and indeed the reason it's true is I suppose that if the law of Y is mu, then I suppose the point is that I can just take mu equal to mu, and we've largely proved this. So it's largely working around to a definition, which is simply that when Y is stable, with law as before mu, we can ask about another law, mu, which is the law of x1 in what we just wrote. If I label that star, it's the law of so right, okay, so if Y is stable with law mu, then the law mu as is playing the role in this star distributional convergence. That is then said to belong to the phrase is the domain of attraction of mu. So if I take a given law such as the standard normal law, then of course stability implies that the standard normal law lies in the domain of attraction of this law. If I add up a large number of independent copies of the standard normal law in the sense of independent random variables, and then divide by the square root of n, then I get back a copy of this law. But of course, many other things in that case also lie in the domain of attraction. If I take, in some sense, any reasonable law, according to the right definition of reasonable, with fast enough decay behavior for its tails, then the central limit theorem tells me that I'm in the domain of attraction of the this standard normal law. So the AN, of course, is its classic role of root n, and then Bn is bears some relationship to the mean of the law that we're talking about. So we're in a way, though, I mean, that in a sense is the most fundamental example of all, I suppose, is the normal law, and that corresponds to a slightly different regime to the focus of this class in a way, because our focus is on the random Devil staircase and on the heavy tail behavior that's needed to give rise to them. And so we're interested in stable laws that have heavier tails than this. And note, by the way, that a stable law always lies in its own domain of attraction. Every stable law has a non-empty domain of attraction because it contains itself by almost its very definition. Okay, so if we believe that we have to move to kind of heavy-tailed situations, I mean, basically a random variable, what is the situation anyway? If I take an IID sequence of random variables with a given law, what is the kind of condition we expect to have a kind of a heavy tail situation? So what I mean by that is one in which we're going to be seeing flat pieces in our random Devil staircase. So viewed on a certain scale, there's going to be a sense that the longest piece should be occupying a macroscopic fraction of the picture. So this picture is somehow the it's a reflected copy of another picture in which we record the heights of random variables. So the kinds of conditions that we're going to be expecting on a law mu, in order that we have this kind of framework, is that we have, in some appropriate sense, this where alpha, the view is it should be between 0 and 1, because that's a condition that's needed to create a circumstance where if I add up n independently picked copies of random variables that have this law, then the situation in which my statistics are dominated by the biggest values, it is this situation. Well, we can look at some, I can perhaps say that more clearly again a bit later. I'm generally trying to motivate why we have a certain focus in what's now being said on these kind of heavy-tailed situations. So, okay, so I'm now going to develop a bit more the theory that's related in a way to the meaning of the symbol. If you're prepared to believe me that we want to study these heavy-tailed random variables, it raises the cousin question of what the meaning of that symbol is. What degree of discrepancy can we have from the pure power and still have a hope of seeing these scaled pictures emerge in law in the random Devil staircase? So yeah, for this is an important definition. So the role of f in applications will be something like the tail of the distribution. So this function in applications, its value at n will be something like this object, the probability that our random variable exceeds n. That will be the kind of role we have. But for the moment, it's just a function. And indeed, the theory of regular variation has many applications, and not just in probability. So here's a certain notion of a degree of regularity, as well as tail behavior for a function. So this will be a statement that's true for all lambda positive. Yeah, so let me say that this equals lambda to the rho. So rho here is a parameter. So this is simply a definition that a function may satisfy. Yeah, okay, so this is called, if you have a measurable function, f, of course, well, let's say it's positive. Well, it's already kind of encoded in the definition. Satisfying this condition, then that's said to be a regularly varying of index rho. So let's just record any notation we might want to take away from this for later. This is coming from the regular variation book of Bingham and Goldie and Teugels. So we just write that regular, the function is in that function class, R sub rho. And then, okay, there's a special case where rho is 0. And here the function is called slowly varying. So in a sense, you can view the general case as kind of composed of two elements, really. You're saying that there's a sense in which the tail of the sequence, if f represents a probability distribution and it represents f of x, the probability that the random variable exceeds x, then I can speak kind of the tail of the sequence. So somehow regular variation is making a claim on both fronts. It's making a claim as to how fat the tail is, represented by the value of rho. And it's making a claim about regularity, that rho is in some fairly consistent way describing the tail, that there aren't, you can have examples of situations with large gaps, so the effective rho value keeps drifting upwards and downwards in some sense. So we don't have that. And then the definition of slow variation kind of abstracts away one of those considerations and just focuses on the question of regular, on the regularity of the tail. So I suppose what I want to do is I want to basically state the main result about stability, and I won't actually, I think, prove it really. I go for a slightly mixed approach about this topic, in which I will prove a couple of nice theorems, and I will state some more, partly with a view to what we're doing next. So if I have a measure on the real line, we are of course sometimes interested in its tail behavior. So think of x as being perhaps positive here. I can study the positive tail behavior of the function by defining this. The plus is intended to suggest the space to the right of x and the value it receives. This is a little bit my own notation. F minus suggests the left tail. So here I study what's going on from minus infinity up to x. Okay, so here's a condition that is relevant when we ask questions about the circumstances under which a law is stable. So a tail balance condition. If you have an extreme event, you could say, of being outside the interval from minus x to plus x, then you can ask what the conditional probability is to be extreme by being very far to the left or by being extreme to very far to the right. And that's exactly what this quantity I'm recording is. This is this conditional probability. Given that we pick a point that's not in the interval from minus x to x, this is the probability that it lies in the left and is less than or equal to minus x, highly negative, rather than the alternative possibility of being highly positive. So if we just say that this converges to some q, the point is that there's a degree of regularity that's being asserted if we write that. This is in the limit of x goes to infinity. Do we have such convergence to a value of q in 0, 1? If we have that, then naturally, if I define p to be 1 minus q, then of course the complementary event will converge to this. Okay, so that's just implied. But the content is in the first statement that there is enough regularity in the tail of the sequence that you actually have this convergence to some value. So let me state this domain of attraction theorem from this text, which is in the probability chapter of the text, chapter 8, from the BGT text. This is a domain of attraction theorem. So, okay, there are two very different types of stable law. The first is the normal law. Okay, so mu, and so mu, I suppose I need, I think the view is that maybe a capital F is the distribution function of mu. So mu is attracted to a normal law if and only if there's a quantity here. I'll just record t squared d mu t. That can be called, as the authors call it, a truncated variance. I suppose it represents somehow with an indicator on minus x to x coming into play. It's the kind of variance given that we make that kind of restriction. So if this is slowly varying, well, that's the condition for mu to lie in the domain of attraction of a normal law. And that's equivalent to this condition on the tail. So this is just a way of writing the tail of being bigger in absolute value than x. So if I divide by a vx and multiply by x squared, then saying this tends to 0. In all honesty, I didn't actually think very carefully about this half of the theorem. It's not my main focus, but I just wanted to state it. Clearly, that's an important aspect related to the domain of validity of the central limit theorem. So,
sorry, what's Vx here?
Vx is the quantity here.
Oh, okay. Cool.
This kind of truncated variance. Okay. So then there are, I suppose it's somewhat implicit in what I'm writing, that there are a class of non-normal examples of stable laws, and we are attracted into them the non-normal stable laws carry a certain index alpha. Perhaps I haven't been terribly clear about its role, but in a sense its role is made somewhat clear by this statement. if we look at this, a probability really to be bigger than x in absolute value, that's what this quantity is this alpha here is positive. So we are considering, perhaps that wasn't clear when I defined it actually. The exponents we consider for rho in the definition of regular variation are negative. And they represent essentially what we're talking about. Laws mu that are heavy tail. The probability that a sample of mu exceeds n is behaving like n to the minus alpha times a further function ln, and that is a slowly varying function. So it has this kind of regularity about it. So, oh yes, so sorry, but that's needed, but then there needs to be also a kind of balance between which way we go in the event that our sample is very large in absolute value. So the tail balance condition holds. So you see that's a matter of deciding what the split between the two terms is, that when x is large, it splits in a consistent limiting way, with q going one way and 1 minus q the other way. Yeah, so in a way, there are certain things in that slightly whistle-stop tour presentation that may be a little unclear. What actually are the non-normal stable laws? I believe that they are, I think the view is that they are indexed by a parameter alpha between 0 and 2, and then by the parameter q in the definition of the stable balance condition. And then I think that they are characterized by those parameters. And then you can write down a nice formula for them using something like the mean of the characteristic function or something or another. I don't actually particularly plan to, at this moment at least, say a great deal more about them. I just wanted to give a feel for how this theory works. We will be using this theory of regular variation in the next topic, the later part of this chapter that concerns sort of fractional long-range random walks. So that's one reason I'm developing it. I guess I want to, the BGT text says that the next theorem is somehow the absolute most important theorem in the subject. So we will use it directly, and I think it underlies a lot of the calculations that you can do with regularly varying functions. It also has a proof that I quite like the style of. So I thought I'm going to be highly sporadic if it's not already clear in this topic in what I prove and what I don't. But I think let's do this one. So this is the UTC, the uniform convergence theorem. Let's just finish the class by stating the UTC, which is somehow the fundamental theorem of regular variation, I think you could say, according to these authors at least anyway. So if I have a slowly varying function, so that means that what I'm about to write down, we have for any positive lambda that this is true. I mean, I'm kind of writing it down anyway because the conclusion of the theorem is a similar form to what it means. But anyway, I'm just restating that this means for any lambda positive we have this convergence. But the result says that in fact that convergence is uniform on each compact, so locally uniform convergence in the lambda variable. Okay, is that statement clear? I think I'll end the class at this moment.